So this is going to be a very interesting practical demonstration on microfluidics by Marina Alistair from the Hassel-Plattner Institute. So without any hold up, I'd like to introduce Marina to carry on. Thank you.
Hello everyone. Thank you for being here. I'm going to shortly introduce myself and my work through a few slides. Then I'm going to use an analog way of teaching, which is using that flip chart over there, to teach you a little bit of formulas about digital microfluidics. And then I'm going to use even a more analog way of teaching, where I'm trying to actually show you how it works in real life at that table. So as you can see here from the title that I chose for today, I've done design automation for digital microfluidics with an emphasis on design automation. My background is in engineering, namely embedded systems engineering. So I dealt with reliability, faults, fault tolerance. We are always wondering what happens if things go wrong. In terms of digital microfluidics or droplet microfluidics, there are two things that could go wrong. One is during the movement of the droplet. Here you can see an unbalanced split, very high, not very high resolution. What happens is if you split the droplet in an unbalanced way, you have the wrong concentration, and that's a transient fault. And here you can see the hardware faults. And during my work, I was wondering, what happens if things go wrong during the movement of the droplets? How can I correct that through software? What happens if some of the hardware breaks down? How can I correct that through software? So I came up with a lot of algorithms. You can find them on Google Scholar, including an online compilation. It doesn't have, okay, including an online compilation. That was a couple of years back. After that, I was thinking, what if we can take these microfluidic devices and turn them into something larger than being used in a lab? What if they could be used by people? So currently, and when I say currently, it's a work that's been going on for like 1.5 years, I'm with the Human-Computer Interaction Department. These are people that are responsible on how you interact with your smartphones. They know everything about interfaces. They know whether moving your finger in the right side or on the left side is better, and everything like that. And I'm working with them, trying to find an interface that would connect a regular person, like me, like you, like your brothers, like your sisters, like everyone that you know, to a microfluidic device. I had to do a lot of things. As I said, I'm an embedded systems engineer as training. So here's me in a lab learning biology. And here's a PCR machine that I built with some friends of mine, and we're doing some PCR, we're amplifying DNA. Then I had to think, okay, I have to bring such devices to people. First, people that need to have such devices were people like myself that were in computer science labs. You know how our labs look like, right? They have some tables, some computers, and some chairs. That's the most we have. Now, I just want to do a survey, like short. How many of you have been in a microfluidics facility clean room? 1, 2, 3. So it's like 20% of the people here. How many of you have been close to a clean room, like seen through a glass door or anything like that?
Any clean room or just microfluidics?
Microfluidics preferable, but any, it works as well. Okay. So you know a little bit about how those facilities look like and how different they are from a computer science lab. So the things that I had to think of is that computer science labs, they don't have so much money. Devices need to be cheap. We don't have $500,000 to pay on a machine that does vapor deposition. Ideally, they should be do-it-yourself, so you don't need to hire specialists for that, and portable. I built such a system that is connected to, this is a tablet, the Microsoft Surface, and one of these droplet machines, a digital microfluidic biochip. The next question I had to ask myself is, you know, you can see the interface is quite easy. You can move the droplets using drag and drop. I'm still working on the system, is in development, but the idea is that it's going to be very, very easy to route the droplets. So the next question I have, what if everyone and when I say everyone, I mean really everyone, will be able to prototype biology. What if these digital microfluidic biochips become the Arduinos for biology? And now I just want you to take like 1-2 minutes and think how Arduinos or this kind of microcontrollers have changed the way we see and interact with electronics. A lot of people, like designers, for example, industrial designers, artists, now prototype their small robots, their ideas that they had in the mind, and before they could just draw them or maybe made them of cardboard, now they can actually prototype using such devices. What if we can have a device from microfluidics which moves and manipulates fluids, and people would be able to prototype biology, whatever that means. So I have to be responsible, because usually what I think and want, I also make it happen. So I'm running a series of tutorials, I'm developing a community of users, and I'm also working on ethical code. This is one tutorial that I gave last year, working as well with children, a bunch of other tutorials. Yeah, Petra is on one of them there up. This is the community of users. I think there is always a place to have your portable digital microfluidic biochip and work with it, or design a new prototype, a new version. Also teach everyone about it. So I carry it with me everywhere, and we have all sorts of gatherings learning about it. And this is a draft of how to use biology at home and what is the ethical code behind it. We are still working on that, also on a Biocommons license. Nevertheless, one not so used means to transfer knowledge and influence people, and that's what we do as academicians, as professors, is art. And I also have art projects. Here I'm having an LG installation, and I'm serving people LG beer, and a lot of other projects that I had with art. Oh yeah, also fashion. We are making hydrophobic clothing, working with Electro Couture in Berlin. What you see here is bio-leather made of a bacteria that is grown over several months, and we're trying to make it hydrophobic and embed some microfluidics inside. Yeah, so you can find me or more about me on my website, personallab.org. Now, as I promised, the next part is going to be on the flip chart. So I need a little bit of a light show here. If we can turn on some lights. Back, yeah, that'd be amazing. Okay. After the flip chart, I promised to you that I'm going to show you a live demo. Now, just in case the demo doesn't work, we all know how these devices work or not. They have a mind on their own sometimes. They're quite automatic. I have prepared a video. So this is what you're supposed to see in the demo, and I'm going to show it now to make sure that you all seen it. You can see here an array of electrodes. Those squares are electrodes. A droplet. The droplet has about 15 microliters in size, and the droplet moves on the array of electrodes. Let's see if I can run it again. Yes. Okay, not even the virtual version wants to run again. Okay. Now, what happens there? So, we have an array of electrodes, right? Maybe we can turn off the, Mark, if we can turn off the slideshow. So there is no projection in here. There is this array of electrodes. Again, this is not a tutorial, this is a workshop, so feel free to interrupt me at any time and ask questions. These are my electrodes, and we have a droplet on top of the electrodes. And when we apply voltage, electrical voltage, to the neighboring electrodes, let's pick this one, for example, and we apply electrical voltage there, the droplet moves from one electrode to another. Now, it can happen in all the directions. It can move here. It can move diagonally if close enough. It can move up, to the left, and again diagonally. So now the question is, what exactly happens there? Well, we have two states in which the droplet can be on a surface in general. Let's say this is our electrode, and we have the two states. First one is when the droplet is popping up, so it's kind of staying up like that. It means that it doesn't wet the surface. And the second one is when the droplet wets the surface. Now, the biggest difference and the way to measure the difference between them, this one is not working anymore, right? Is it okay? Is by looking at the angle. There is a contact angle. This area here is called the three-phase contact line, and we have an angle here, this angle here, and we have another angle here. If the angle is larger than 90 degrees, the surface is called hydrophobic. If the angle is smaller than 90 degrees, it's called hydrophilic. Now, what happens at the surface level, that's a nanotech domain. It was observed on the lotus leaf. The structure is bumpy, and the water droplet stays in between bumps and goes from one to another. Research labs, such as the one in Twente, Physics for Complex Fluids, are trying to make an omniphobic surface that even repels not only water, but oil as well. There are two ways of repelling this. First is beating it, making it stay, and then making it also, allowing it also to roll. So what you guys are going to do right now is that you're going to form teams of 3, and each one of you is going to get a cup. And in the cup, you're going to have water. And this is this kind of water, so I'm not sure what's inside, but I'll just assume that this is the closest we can get to water here. And I'm going to have a pipette, and I want to challenge you to find the most hydrophobic surface you have around. So look in your pockets, go around, try out all sorts of surfaces, and when you find something that looks really cool, the droplet really pops up, it has like a very nice angle, then call me and I come there if it's not transportable, or if not, we can transport it here for everyone to see. So if you can all pass around, teams of 3, and also you're allowed to talk to each other, so there's no problem about that. He's too busy to do droplet work. I'm Mirella. Nice to meet you. Okay, I can help you with that. Okay, one here. Ta-dum. Let's go some randomness. Leave the computer away. Pipette. You can give me back. Yeah. Go get water.
Sounds like a great idea.
Anyone missing water? Okay. Yes. Oh wow, that's not bad at all. I like it. Leave it here for. Okay, that's not bad at all.
Oh yeah.
I'm not happy. They're much better. Okay.
This thing after a while, if you put it like this, in the beginning, it's
Yeah, because of the structure.
done.
Then the pores start sucking it out. You go and compare. This is what I've got so far. Yep.
Yeah.
Yep. Still have some work to do. Is it a watch? Oh, your rain is coated. Your rain jacket is coated against water. Nice. Not bad. Not bad. Not bad. The rain. What have you guys tried? Yes. Oh wow. That's not bad. That's not bad.
This is the most one.
Nah, yeah. What's your name? Shreyash?
Yeah.
Or Shreyash? Shreyas. Shreyas. Andrea?
Shoe, but it doesn't work.
Your shoe. Don't put it into rain. No? Okay. Cell phones. Have you tried cell phones? The Surface. Okay. Is it waxed? Is it waxed?
That's the best we got.
Whoa! It even rolls, not only beads. That's amazing. Not bad. Not bad. Okay, guys, I've seen a bunch of tryouts. So apparently Shreya's jacket is the best. So don't forget to take I have a scissors here. Don't forget to take the scissors and rip off some of his jacket to take it home to prove how hydrophobic can it be. The whole point is to try to look at things around us, especially small things like fluids. We all know that microfluidics happens because fluids behave differently when they are small than when they are large, right? So the principles that we have in physics for large fluids in tubes, they don't work the same for microfluids. And I hope you can all see now fluids through a different angle, that is the contact angle, when you look around. Now, I showed you a bunch of electrodes and some droplets moving from one electrode to another. I'm going to show you how these electrodes can be made. In more scientific terms, because I'm going to be forever on YouTube, what is a potential substrate for the electrodes? Well, the one that you saw, which is PCB based, and I'm going to hand this over so you can take a look at them. I've tried here with different sizes and different gaps between electrodes, so getting them closer and closer and closer. All of them are home etched. So there is a difference in using a machine to etch them. Etching means removing the copper and managing to get the right pattern, or you doing it at home. And here I'm playing with a lot of different types of electrodes. So I'm trying triangular ones, I'm trying comb ones, I'm trying, yeah, you can see around. So if you can pass this around and we can take a look for like a couple of minutes, different patterns of electrodes on PCB. But it doesn't stop there. We can have paper-based electrodes, and here I have it on acrylic just to make it stay still. So like to have a straight surface. These are made of silver ink. They can be printed. In my case, I was brushing them with a pen brush and laser cutting them. So these are silver electrodes. I'm going to pass them around as well. Here we have another device, printed, this time printed silver electrodes on a glass stand as well, just to keep it straight because it's paper. another silver one, so I have 3 silver ones that I can pass around. Now again, ask me a couple of questions, if you have any at this moment. Yeah? What's your name first?
Tahwa?
Tahwa, yeah.
So probably everybody knows the answer to this, but what is the application of moving droplets over?
Oh, we're gonna get to that. Yes, it's true. What can I do with moving droplets? That's good. Any questions about technical things? Yes?
Does voltage somehow affect the cells if you are looking at cells?
Yes, so, okay, how to phrase that question, that answer. That answer is related to what can we move on such a device. And hold both of the questions when we go to the practical stuff, and I can show you an example of what can we move. I'm gonna come back to those questions. Yeah?
Could you merge a drop of water?
You can merge and mix droplets of water in a topless biochip, so on a topless device without a cover, but you can only split without a cover if they are immersed in oil. If they are in air, you need a cover, a top layer. And the top layer can be an, how do you say, an ITO glass, for example, transparent. So the next type of electrodes I'm showing to you, they are here. You have to look at them from a different angle so you can see them shining in the light. They are etched on an ITO PET. ITO, indium tin oxide, is a conductive that is...
Write it down. ITO.
Of course. ITO PET. So PET is the plastic, right, that we all know, and ITO, indium tin oxide, is a conductive material that is transparent. Now, transparency matters a lot because to answer her question, we want to do biology with it. We want to mix blood, urine, do glucose assays, and we need to have some sensors. We need to be able to read out colorimetric reactions. So transparency is very, very important, especially having a top layer that's transparent, ideally and underneath as well, because you may need to have some light source for fluorescence. So you can have glass-coated ITO and you can have PET-coated ITO. We're trying to use paper and PET because we're trying to make these things disposable. Ideally, you have a glass substrate. You can have chromium glass, but that requires vapor deposition, very expensive tools that we don't have in a computer science lab. However, we can buy a bunch of chemicals and etch it using ITO PET. So now I challenge each one of you to look like in the right angle, and you can see that the design is quite complex and you can have very thin lines. There are 2 different designs of electrodes. It's hard to see, I know. And the latest paper type of electrodes are using carbon nanotube ink. Cool. They're very cool, I know. So you can also print a different type of ink that aligns carbon nanotubes in a conductive way. It's also printable using an inkjet printer, like an Epson printer over the counter. So these are different ways in which you can have the electrode substrate for the droplets to move. And as you probably already figured it out, I'm trying to show that it is possible to do hands-on microfluidics, not only at theoretical level, but also at practical level, even in a computer science lab. So everything that I'm presenting here is work that can be done by a computer scientist, by an electrical engineer, by a person that doesn't have access to all these clean rooms and facilities. Now, what exactly happens? So, we have our electrode, and we have our droplet on top of the electrode that is under electrical voltage. And as I said, there is a 3-phase interface between the liquid, the vapor, and the solid. So now at this contact line, there are 3 different tensions that work. forces. For the phenomenon that happens when the droplet rolls from one electrode to another when applying voltage is called electrowetting on dielectric. In short, is EWOD. You probably have heard of it. Electrowetting on dielectric. There are 2-3 explanations of why this is happening. There's a lot of labs working on the explanation for it. One explanation is the electrohydrodynamic principle. That's a bit too complicated. I'm going to go into the thermodynamic electrochemical explanation. So we have here at the contact light 3 different surface tensions. We have the surface tension between the liquid and the vapor. We have the surface tension between the solid and the liquid, and we have the surface tension between the solid and the vapor. There are the 3 surface tensions. And we have our magical angle that we already know about. And Young's equation says that in order for the droplet to be in balance, in its balanced way, cosinus of this angle is the difference between the 2 of these over this one. So if we like draw one of these here, and it's a 90-degree angle, we have the difference between the 2 of them over the hypotenuse. So that's cosinus of the angle. That's Young's equation. Now, this is a thermodynamical explanation, what happens there at mechanical level with the forces. Now, if we go into the electrochemical formula, Lippmann equation says that the surface tension between the solid and the liquid, so what happens in the droplet when we apply voltage on the solid, on the electrode, so at voltage, is the surface tension when there is no voltage minus the capacitance square voltage over 2. This formula looks familiar. You can find it a lot in electrical engineering. And now what happens is that in between the electrode and the droplet, there is an insulator layer, right? You cannot have the droplet directly on the electrode, otherwise you have sparks. So at this insulating layer, the layer is dielectric. The way that the ions arrange is described in this capacitance, and the capacitance value is the dielectric constant over T. In this case, T is the thickness of the layer. Thickness. Now, if I put all of them together, can everyone see here, down here? Okay. So I have cosinus of theta equals, and then I start replacing in this one. I replace it with this value here. So it's V minus LV. And here's a 0. Now this is cosinus theta 0. So it all leads to, okay, I'm going to do it here so you can all see. Theta, well, cosinus theta 0 plus, I'm replacing the capacitance with this value, so we have V squared 2. Now, this is called the Lippmann-Young equation. And why is this so important? I'm going to write it down again. So have you taken all the pictures? Okay? I'm going to write it down again because it's very important. I'm going to show something on it. Again, we have our electrode, we have our droplet, and we have our forces. Well, not really like that. Like that, like that, and like that. We have our theta. This tells us how the angle changes, how the droplet changes from popping up, from not wetting the surface to wetting the surface. And the change, initially it pops up. This is when there is 0 voltage. And the new angle depends on epsilon is the dielectric layer, the dielectric constant of the layer here. T is the thickness, and V is the voltage. Now back to your question. We can have very high voltage here. I know people that have been trying to, and you can see them on YouTube, trying to move droplets with 700 volts or even more. I'm not joking. I mean, people want to see the droplet moving. They know the principle, and if you're desperate, you want to get this angle as sharp as possible, so you increase the voltage. And you can see that the voltage is the most effective way to do that, right? It squares, and then you have higher angle. However, if we're working with samples like cells, we may be concerned about that. And since we're operating with those devices and we want to have them running for an hour or two, we don't want to have super high voltage because electrons can also jump from one electrode to another. To give you an idea about dimensions, these electrodes are usually 1 to 3 millimeters in, how do I say that? Yeah, in size. Pitch, electrode pitch is called. And the gap, in our case, because we do PCB etching, is like 0.1 millimeter to 0.2. But if you do chromium deposition, it can be 1.5 micrometer. So they're very close to each other. It happens, I mean, if you have high voltage, the electrons can jump from one to another, the gap, and you can have sparks. So, since with the voltage, you want to keep it in what's the lowest as possible, let's say like that, and the lowest as possible is in today's papers or operational devices, 90 volts to 260 volts. That'd be something. Usually 90 to 110 volts. That's what it works. DC. The only things that you can tweak around are these two. They depend on the layer in between and liquid vapor interface. So we usually want to move them in air. The reason we want to move it in, well, let's put it like this. It works better if we move in oil, since we are targeting aqueous droplets, DNA that dissolves in water and stuff like that. Then it's better if we move in oil, because this value is much better. However, if we have cells inside, cells, they have oily membranes, and then they dissolve in oil, and then we want to move them in air. So there are two ways to work with this equation. One is trying to get as thin as possible coating. And when I say thin, it's maximum 10 microns. So even thinner than 10 microns. Then we're trying to get a coating with higher dielectric constant, but insulating, because I don't want sparks in between these two. And then we can also try to work with the interface between the two of them. And in order to move water in air, for example, there is a class of chemicals called surfactants. They only wrap the droplet around like a detergent. They don't go inside and change the molecular structure. So then you can change the surface tension only. It's quite difficult to work with them. Pluronics is a class of surfactants that you can work with if you want to. Okay. Let me take a little deep breath and then continue. So that's a little bit of intro of how the physics of small, tiny, complex fluids works. At least, a small equation. If we go in details, the equations are like as long as 2-3 rows. What we're going to do next. We're going to come closer, so everyone is going to stand. So I'm going to take like 2-3 minutes of break, and I'm going to explain what is going to happen. Well, everyone is going to stand around the table. I'm going to show to you one of the first prototypes that we built. All the design files are available open source, so you can just order the components from China. You get, 2-3 weeks, and then you assemble them. It's soldering I mean, I guess almost everyone knows how to solder or surface mount components. If not, it takes probably one day to learn how to do it. These electrodes, they have underneath, through hole, each one of them a transistor, mini transistor. The transistors are controlled by Arduino, connected to a power supply that takes the 12 volts from a regular power supply and adjusts it, steps it up to 260 volts. It's adjustable, so you can adjust it with a potentiometer for each application that you use. And then the Arduino can be programmed from the computer, and you tell the Arduino, I want this electrode on, or I want this other electrode on. So this is pretty much how this works. And there is an advanced version as well, a little bit more advanced, which has direct control for real time with a joystick. So there's joysticks, and then also a display screen that shows where the droplets go and how they move. So after 2-3 minutes of break, you can come here, ask me everything about the technical details, how I implement it, how it works, and then I'm going to try to move some droplets on, and I'm going to show you the following. I'm going to show you some German water being moved on. It has to be German. It's the best water. It is tap water. Distilled water would work as well. I prefer to use tap water because it's a bit more personal. And I'm not joking. Tap water is very different in a lot of countries. So German tap water works, Swiss one doesn't. And that's a local joke. Then I'm going to show mixing two inks. So we have red ink and blue ink. And that's what's interesting when you mix two droplets, is that mixing is not the same as merging. When they meet, they merge instantly. However, there is a flow inside. These fluids are very, very small, and it takes them to move in a circle, in a certain pattern, for a certain amount of time to mix. And you can see going back and forth. You can see the red going into the blue and then going back and becoming a little bit more red, and at the edges being still blue until it really becomes the purple that you need. Actually, if you move two droplets that are mixed to one electrode and back again, the demixing happens because there is a reversibility in the flow. If you move them too close in a loop, there is a yolk inside that never mixes. It looks like an egg, only the outside mixes because it has only one pivot around it which it mixes. So there are students, and I can tell you the names if you're interested, that for 4 or 5 years of their lives they study two droplets moving and what is the best pattern for them to mix homogeneously. This is for colors, to answer your question. So you can see electrowetting was, the first application was in displays. So using and mixing colors to make displays, to show all sorts of things like that. You can have very precision color mixing. Now, I'm going to show lately, the last thing, I'm going to show my DNA being moved in aqueous solution and a piece of plasmid that I designed myself. And hopefully they're going to mix as well. So these are biological samples. And the idea is to be able to use for biology. In order to move proteins or cells, it becomes more complicated. We need surfactants for that. So because proteins tend to stick to the surface, and then it works for a while until they contaminate the surface, and then you don't manage to move them around so well. So at cellular level is not yet too advanced, the technology. There is still a lot of microfluidics that needs to be done. At DNA level is different because DNA is water soluble, and then we can move it in water buffers. So synthetic biology and procedures around synthetic biology can be done quite easily on the platform. Okay. 3 or 5 minutes break, and then we come back.
Well, you said that the proteins stick to the surface.
Yeah.
But if you can increase this, is it possible to increase this? I have no idea.
If you increase this, then you don't get the contact angle to change.
That's true.
You need to have it as small as possible.
It doesn't work anymore.
Yeah. So you need to have like 3 microns.
Right. Same for cells, actually.
For anything.
Stick as well, cells, through receptors.
So cells have with cells it's a bit more complicated. With cells, the droplet is not homogeneous.
It's not.
Yeah, and it stays to the bottom. So even if you grow them in liquid culture, right, you see them sinking at the bottom all the time.
Unless
And so you need to kind of have some kind of vortex that mix them all the time, and you don't have that in here.
unless you can take a kind of a gel or something, but if it's a gel, then you can't definitely.
If it's a gel, then these formulas don't work anymore. It's a different state. It's not a liquid state. So I'm going to Bristol right now to try to move them using ultrasound. And there, for example, mixing is not a problem because of all the ultrasounds inside, they mix instantly, but their splitting is a problem. And also ultrasounds are different frequencies that may affect the cells as well. So we're trying to see if we can combine the two platforms and have part of it using ultrasounds and part of it activating it.
I see.
So, oh wow, that's loud. Thank you, Marek, for adjusting that. Okay, so if everyone that's interested should stand up and gather around me. So as I showed you in the equation, what we have in between the electrodes and the droplets matters a lot. And there are different materials that we can use in between the electrodes and the droplets. We can use a very thin coating of Teflon, for example. There are about 4,000 types of Teflon. And the one that is used is Teflon AF 1600. It costs a lot. It's like €1,000 for a very small thing, and it has to be spin coated at a certain speed. So building a spin coater is not complicated. You just have something that rotates, put a droplet in between. I don't know if you know how spin coating works. You just put a droplet in between and start spinning at a certain speed. First slower, then faster, then slower again, and then the droplet spreads around in a very thin layer. When I say thin, I mean 3 microns to 7 microns. However, if you remember, my vision is that everyone is going to be able to have one of those. So asking people to spin coat at home using Teflon is not really a good solution. Then you can use a mix of different foils with different chemicals, and I can go through a lot of lists that I tried out. Some of them need baking as well, so you mix Teflon, for example, with Perlin C. Teflon is the insulator and dielectric, Perlin C is the dielectric, and you have a certain mix. You spin coat, and then you bake for 8 hours, and then it runs for like 3 minutes before it gets contaminated from the dust. So, from the dust in the room. So we're thinking, okay, what can we have that is cheap, doable at home? Contamination, there is something that we cannot do much about it at the moment, but the idea is that it would be cheap, done in a couple of minutes, so people don't get too discouraged, and they could learn it from watching a YouTube video, and then it could be thrown away, and then we solve the contamination problem. We don't have to replace the electrode array, because I told you about all these paper solutions, and the idea is that here you dispose of the electrode array. And they're like, okay, we have a PCB one, we don't want to replace all the time the electrode array, maybe we can just replace the foil on top. So we looked around and we ordered, like in my lab I tried out like at least 30 thin films, PTFE, TFE, and I can give you a lot of, varying from 13 microns to 50 microns. 13 micrometers to 50 micrometers. So there are some problems. These coatings are usually used for aeroplanes. So people are not used to, when we finally decided for one, they were not used to fabricate only 100 meters. They wanted to give us 200 kilograms of foil. And I was like, I could coat all the biochips for the next 100 years with 200 kilograms of foil. The second thing is that some of them, they deliver samples in huge, rolls, and they were holey. They had holes in them. Because for an airplane, probably a 1 femtometer hole doesn't matter, but for me, it's enough for my electrode to jump around and make a mess on my biochip. So eventually, we ended up using kitchen foil. I can name it in many languages, most of the languages where I gave my workshops on it. It has a very nice dielectric constant, a thickness of 10 microns, so it's just enough to use it on a microfluidic biochip. I'm not saying this is the final solution, this is this current solution. Now, the foil is the insulator and the dielectric. We are coating it on top with silicone oil. Now, silicone oil is a very low viscosity oil, lower than water, but there are also about 400 types of silicone oil. So the viscosity matters a lot. Remember that force that we have there is surface tension between what we have in between. And this is silicone oil 5 CST, so viscosity is 5. It's really important. If you use 1, it doesn't work. If you use 250, it doesn't work. Viscosity is very important. Okay, I'm gonna pass this around, take a look at it, and ask questions. I'm listening.
Do you guys ever get worried? Oops, sorry.
No, please go ahead.
Emergence, I love it.
No, it's always.
Do you guys ever get worried about like the high voltage nature of the device, and then you're mixing fluids, and then the DIY aspect as well, or?
Yes, we are.
Okay.
Yeah, we are. So the good part is that electrowetting is not so easy to make it work because it's the interface between microfluidics, electrical engineering, and also computer science. So our user base usually gets trouble making it work. So then we kind of have a way to always, I mean, they always come back to us for questions and stuff like that. So we always know what they're doing, what are they planning to, how trained they are, and we encourage the ones that have no knowledge, for example, to couple with the ones that are, so biologists, for example, they don't want to bother with this kind of stuff, they could couple with some engineers and work together on projects. And the engineers that love to figure out why the electrode doesn't move or doesn't work, then it's a nice mix. But they always have,
Going then.
we have about 100 people interested and 80 that are in touch with us like weekly base. About I just wrote a journal paper on that. About 30 attempts to replicate it and 15 successful. The 15 ones, they're like 30% of academia and 30% industry, and the rest are makers, spaces, or individuals. I know all these numbers because I just had to submit the paper 2 days ago, and they're asking for specific numbers. But of course, the list always updates, so we always receive emails or, I mean, this is what we are aware of. We don't know what's happening there. However, we didn't invent electrowetting. Everything about it is already patented. So people have been trying to do electrowetting before in many, many ways. So if you go on YouTube and look for electrowetting, there have been videos for 10 years ago, people trying to move droplets on electrodes like that. So it's as simple as this one. The first time we moved droplets, actually, the very first was this one. This is the very, very first one. So what we did is that we put a Scotch tape on it. That was our insulator. The thickness is very big, so it's too thick. So we had a glue gun and made a well around with glue, and then we poured oil, and then you need to find the right type of oil with the right type of droplets. So we mixed about 400 combinations of oils that we have, all the oils we had in the kitchen, all the droplets we could find at home, until we could move and split them by manually applying voltage on each electrode. So using a power supply that I built and then manual applying. And people have been doing that in many ways. So, I mean, a step-up converter is this one, right? And all you have to do is to open an electrical engineering undergrad manual of first year and copy the circuit. And with the techniques we have now to do that, anyone can have, or you can order it from Amazon for €10, actually. It comes like that.
Question. So, do you need 90 volts at least for each of those?
We're using more here because I'm not going to operate with a top plate, so we're going to use 250 volts.
250.
Oh, sorry, I'm covering this one.
It looks a lot. Is it,
A lot
if I
for.
touch it, what happens?
Well, if you have a good insulator, nothing will happen. If you don't have a good insulator, I'm going to ask an undergrad student around to explain what happens.
So we better stay.
I don't think the electrons can jump over there. I'm the one that is a bit in danger. So it can happen, anything that can happen when you work with electrical voltage. Yeah, there is a question about safety, of course.
But wasn't the interaction of voltage with the sample that you're moving with your droplets, isn't it possible that the voltage might damage the content of your droplet?
Yes, so that possibility exists. However, it's very hard to test it because at the moment we are not there where we are moving cells.
Right.
So cells will be the only ones that are really endangered by high voltage.
Sure.
And
What
DNA?
about
DNA is fine.
Okay.
Yeah. At least on 90, 110 volts, I can guarantee is fine. So more than that, no. Again, I didn't put the equation for the speed.
To make more room.
Oh. I thought you're leaving, and I was like, okay, am I so bad? So, what was I saying? 90, 110 volts. DNA. I don't remember. Yeah, it doesn't damage the DNA for sure, because there are several protocols there.
What makes sense?
Proteins are tricky to be moved. There are only 2 or 3 academic works that moved proteins, and I'm not sure how replicable they are. So yeah, so I'm advertising now my papers, but my latest paper that I published is on this device. And since this device has been there for already a couple of years now, and a lot of people have replicated, including a few labs from MIT and stuff like that. I was like, how can I motivate my work? Because everyone wants to have like new work that has never shown to anyone. And I was bringing the motivation of replicability, because we always make things that are not reproducible outside of the lab. So I was like, we wanted to test our platform to see if it can actually do it yourself, if people can replicate it. And we needed years for that to see how it's going to go. Okay, let's get going. So, here I'm going to disassemble it. And as you can notice, I'm not working in the most sterile environment. And every speck of dust matters. It changes the surface. So I really hope it's going to work. Now, I'm using this cartridge thing as a cover for my underneath coating, so kind of protected from dust. If you look it has a lot of dust specks already collected on it. So when I'm traveling, I'm just putting it here. So hopefully when I take it out and show it, the coating is still intact and it works. If it doesn't work, you may have to bear with me because I'll have to redo it. But it's a live workshop, so things happen. Okay, so here we have this coating is a foil. So if you can look in different lights, you can see it. It's this foil. And I'm trying not to derange it too much. I'm usually using gloves. It's necessary because sometimes the oils in your hands, if you use bare hands, can affect the surface. And I'm trying to see if I have a lot of dust or not on top. There's also silicone oil on top. It's okay, you can speak loud. Okay, taking a pipette and water. How many of you guys work with pipettes in the lab? 1 or 2. What are you guys doing?
Cell-free reactions.
Reactions, okay, good. All of you, or are you from different labs? Different labs.
We've got about maybe 7 labs that are there right now.
Is it easy to clean it from
They have
dust?
lots of them in there.
No, I'm trying to run it a little bit and see if I can clean the dust on top. No, it's not. I mean, usually you redo it, the coating. I'm just trying to see. I'm just hoping it's gonna work right now. No, it's not easy. And of course, there are better solutions than that. I'm just showing the solution that it's easy to apply in. No, exactly. In a situation where you have 50 people staring at you. Okay. So it's on. Okay. Now the LCD turns on, and I have a switch for the high voltage and a switch for the program. And let's see if it works. Of course it doesn't. But you saw the video, right?
Just once.
Okay, I can play it many times. Not twice, not even that one. Doesn't work. It's a realistic video. Doesn't want to work more than the real one. Okay, So I'm trying to prep this second one and trying to see if maybe the second one works, and if not, I'm redoing the coating. But don't worry, you're not gonna. Yeah, of course.
There she go.
You're not gonna leave here without seeing droplets moving. I promise you. Even if I have to make one from scratch until tomorrow. Okay. So everyone has seen it. Take a look. Now it's stuck. What it gets stuck? When it gets stuck, it can be for several reasons. One reason could be that there is a speck of dust there, so the coating needs to be changed. That's the first thing. One reason could be that there are proteins that are bound to the surface, so again, the coating is contaminated. Another reason could be that the electrode underneath has been overused, so it's deteriorated. Another reason could be that the dielectric layer is broken because of overusage. So the dielectric layer overcharges at some point and then it breaks down. It's called dielectric breakdown.
How many cycles do they go for? How many cycles you can use electrodes?
Yeah, so there has been some tests trying to see how far you can push it. 4 hours it worked once in a lab, so no, not so much dust. Let me try to help this baby. So not so much dust, and in a proper lab. Well, proper lab, like a little bit more confined lab. It is quite good to have it working for 4 hours continuously. It's not bad. Interesting. Okay. Okay. I'm trying to set up this one. So you can see water being moved. And the higher the voltage, the faster it moves. So if you lower the voltage, it goes slower. And I want to show to you as well, if it works, 2 droplets mixing. That's something I also promised you I'm going to show. Now I'm a little bit slow because I have to handle a lot of things at the same time. The ones that work in a lab know that the way you handle things is very important, and the order. So the ones that now I have here ink. It's blue ink. It's actually methylene blue. The ones that work in a lab, maybe they can tell a bit more about that. It's a dye that stains DNA. So I mixed it with water droplet, and you can see that it's not fully mixed. It's like darker on one side and lighter on one side. It's very hard to see, so I'm going to put another color in.
It's cool you can pre-program a protocol. How do you interact with the device to do so?
Yeah, that's a question that everyone in the room, I think, can answer. They're computer scientists. So right now, let me show you the mixing. Don't forget the question.
Gotcha.
Sorry, I'm trying to focus. Yeah, I have a couple of videos showing different types of programs. I put too much red? Yeah, too much red.
So you put them all together, and by the movement you want them to mix.
Yeah. I just put one on the path, and then it comes and collects. Because I think there is one that is coded with different programs, and I can switch between programs, so I can have 2 of them coming together and mixing. Which is that right now I don't want to do too many things at the same time. I'm trying to make it easy for me. Yeah. So droplets can. What's wrong? Is it too big? No. droplets can mix. And here we have ink, mixing. And I'm going to try to show you DNA as well. So let's try to stress it until it breaks down. You can see it changed the color. So it changed from, we have initially this pink and this blue, and then it got a little bit purplish. So maybe it's not visible when you look at the droplet, but for sure it's visible when you put it on paper. Now, somebody asked me in the break, and I think I didn't specify it perfectly, but maybe you can see it here. The droplet has to cover the electrode and the cap between the neighboring electrodes. So it has to be a little bit larger than the electrode at the contact. So the size of the electrode, that depends on the technique we use to make the electrodes, determines the size of the droplet at 1x level. You can move 6x, I think I stretched it out with 6x droplets, and depending if you use a different technique for electrodes like TFT-based electrodes, then you can move 250 electrodes droplet, but they're very tiny. It's a different technique that cannot be done at home, unfortunately.
Wouldn't a design of the lattice hexagonal being better in terms of?
There have been some tries out. I have not tried it. Somehow, so you can see that these electrodes, I mean, you can take a look at the other one. They are kind of intertwined, right? So they are not squares. They have this zigzag okay, I'm going to show this one and come back to your question. You have a question and you have a question, right?
So general questions at the end, right?
Huh?
General questions at the end.
Yeah, just let me focus a little bit. I'm tired. So I have one thing to show, and then I answer all the questions. I have here my DNA. I extracted my DNA. And that's the DNA in water solution. Okay, so there's something wrong with that area over there.
How many DNA molecules do you expect to have in something like that?
All of it.
There's high redundancy.
How many?
There's very high redundancy. I don't know how many, but it's enough.
The whole genome.
It's more than enough. It's very small. And here,
So thousands? Or
You mean in kilobytes?
no, how many? How many? How many?
Chromosome or genes? The
How
whole
many?
genome. You can put all the genomes which is in a cell in a droplet. Right?
Many copies.
Yeah, more than
you're asking how many copies?
no, that's
I really don't know how to. I don't know the answer to that, but a lot.
But it's mostly water.
yeah.
Yeah. Baby work. Okay. So until we figure out those numbers there. Actually, that's a good question that maybe a lot of computer scientists, they don't know, and it's better to figure it out. Also related to why is it this useful. There is high redundancy of biological material in our fluids, which means that they're very condensedly packed. And in short, a small droplet is more than enough to run the same things that you can run in tubes. And if you can use less reagent, if you can use less samples, then you also lower the costs, but you also lower the time to result. Because everything mixes based on diffusion, and diffusion is proportional to square the distance. So if you make the distance smaller, then you get square time, the diffusion time, faster. So that's very, very important. Making things much smaller helps everything diffuse in there, everything at small level in biology, things meet through diffusion. Okay, so I have my DNA. What I want to show, I have my DNA here, and I have a plasmid in here. It's a very simple backbone. Plasmid contains lactate. That's a gene that synthesizes milk protein into beta-galactosidase. In regular terms, if you are lactose intolerant, you don't have lactate. And I made this one. You can design it. You use a software tool. You design. You put together nucleotides. I know for you guys this is common sense, but some people don't know. You order them. They come in an envelope, and in Germany they even come to your neighbors. So you have to go and knock at your neighbor's door and ask for your own DNA. It is a little bit creepy. And the reason it's blue is because I mixed it with some syrup. I had an art performance, and it's difficult to convince people you have DNA in here, so it's easier to convince if it has some color. But I mean, they could as well be both in color, I mean, not colorless. Now, the LACZ, I used it I ran a course with 5 artists. They wanted to become bioartists, and I said, well, if you want to become bioartists, then you need to learn biology. So I ran a course of 12 days in Helsinki. They have a fully equipped bio lab there for art. And we did synthetic biology. We modified genetically bacteria to contain LACZ. Also, the reason I put it in blue is because LACZ reacts to, well, the product beta-galactose reacts to a sugar and it gets blue. So when you modify genetically something, you need to also see to measure that you did the modification. So you usually use some kind of modification that gives you a color feedback, either fluorescent feedback, either color feedback. I chose color feedback because it's easier to notice. And in this case, the bacteria that should be modified should have become blue. Another thing that maybe you don't know is that in synthetic biology, when you modify bacteria, you also mix them not only with the genes that you need to change, but also with antibiotic resistant genes, because you want to select for very strong bacteria. So you work a lot with ampicillin resistant bacteria. Anyway, the artists were really cool and we made it work. And then I took the plasmid that I made, this LACZ thing, and I took it back to Germany, and I wanted to make a proof of concept, what it means to modify genetically and how the regulation should look about, because in Germany everything is very regulated. So I had a performance in which I poured it into, the other person that I was doing the performance put it into wine and drank it, and he's lactose intolerant. So technically there is a chance that some of the cells, some of the E. coli inside his body can become competent. That means that the cellular walls are broken enough to take in the new DNA and be modified genetically. There's a very low probability, but there still exists this chance. And that's okay according to the law, because you're doing things on yourself, and that's okay. However, the next thing he did, he grabbed me and kissed me and transferred that DNA to me, because it's as short as, enough to do this kind of things, to transfer. So we're talking a lot about the implications of what we're doing, and since we're talking about bio that spreads on its own, that has life on its own, we're talking a lot about that. But now let's try to do this. So my DNA is on there. I'm trying to move it. Yeah, the surface is not very straight. Okay, apparently it refuses to work. Yes, so as you can imagine, I spend a lot of my time watching droplets. And I'm not even joking. While my students develop an interaction way with the droplets, I'm going to come back to your question as well. So I'm trying to get the backup one to work. No, not this one either. Okay, so we have my DNA moving. Yes, it's moving. I'm trying to see if I'm imagining it or not. Sometimes I imagine that they move. And then I'm trying to move my plasmid as well. So you can see it mixed with the plasmid. Okay, so I showed plasmid, DNA, colors, and water being moved on the biochip. One question was interaction. Okay, so this thing, let's start with the basics. This thing here has an Arduino. An Arduino is a microcontroller that has very easy interface. So when you plug it to a computer, it has an programming environment, and you can write some bunch of code and program this.
Do you program it directly into the firmware, into Arduino? Okay, cool.
So we built a library for it, and you can program it directly in Arduino. That's one way to do it. But if you don't have all that knowledge for that, we're building right now, and it's half working, drag and drop interface like I showed there. So you have your tablet and you just drag with your finger droplets around, and then it shuffles the code into Arduino directly. It's built on Unity. It has a plugin for the Arduino. It shuffles it into that, and then you have it. The new version we are trying to build is to have wireless control, because this one is cable based, and we don't want to drive high voltage in our computers. So that's why it doesn't really work. It either works with that or with the Arduino, not both at the same time. So we thought about our devices at least. We are debating what is the best way. So right now, for example, the idea is that the interface, in the user interface, the visual one, you select the device you have, the array of electrodes, and then you start tapping, double tapping, and creating new droplets, typing in their names, mixing them, putting them together, splitting them, all by drag and drop. Technically, when you're doing that, you're creating a bioprotocol, and you're also routing them. That's practically. Technically, we have a lot of algorithms that can route directly, automatic routing. I've been working on a couple of them as well. So can we work at a different level with the bioprotocol that doesn't necessarily have these visuals with droplets around? And that's what I'm trying to figure out, if there's a way in which we can visually control bioprotocols. There have been two proposals for that. One is a biocoder language and ANFA language. They're all programming language looking a lot like C. I believe that biologists should not program. I think that they should have a different way of interacting with design and bioprotocol, not through programming languages. Other questions? There are some questions here.
No.
It's nice that from molecular communications point of view, you're really able to carry a lot of information.
Yes.
At extremely long distances for us. It's quite a distance for us. But what I'm still concerned with is not voltage. So I'm trying to think of how this approach could be used in practice. Probably not in body with that much voltage, because it's
So like inside the body?
yeah.
No.
It's too power hungry and also quite dangerous, of course. 220 volts inside the body.
So if you're thinking of embodying it or embedding it inside, no. Regarding, this is microfluidics, so it's a little bit different than molecular communication. So we're trying to bridge the two of them. I'm going right now to Bristol, and we're going to try to move droplets using ultrasounds. And the idea is, can we build a device that you can have on top that will start moving the fluids inside your body while you have it on top of your body? So we're trying to see if this is possible as well, especially in the capillary channels. There's a lot of microfluidics there. It's the continuous flow microfluidics. but not with electricity, no. Not electrical voltage.
Do you have any plans for automated liquid handling to load your gas or?
Yes, so we have a prototype as well where you have some capillaries and they automatically load it, and yeah, there are some designs in which we can just plug in small reservoirs and then they'll dispense automatically.
Do they also use Anta, for example, the standard languages? Can you also program them as well? Oh.
Yeah, there's an interaction thing, certainly.
Other questions?
It's always a single droplet.
No, you can move to droplets as well. You just need to program it.
I mean, you have this field called Morpheus computing, which allows you to get pattern formation, all these kind of things, which I wonder would this be possible with this kind of technology? Yes or no? So until now, it's mostly based on the screen, on visual things, saw patterns and mixing and all this kind of stuff. And the people developing algorithms to actually do stuff with them. How close are you, or is this even feasible to do at this?
I mean, I think everything is feasible. I don't know how long it is going to take to be done.
Hard to scale because now you have a very small chip, but if you want to have like a
Yeah, so I want to.
size system that actually allows you this kind of stuff.
Yeah, so I want to build 1,000 by 1,000 array, using a little bit of different technology. I mean, same principles, but a little bit of different technology. And then the main application would be in visuals and displays, so displaying information. And also we're thinking of printing. We're thinking of tissue printing, because usually you have this modified 3D printers that have like sequential stuff. Here you can have parallel stuff, but not only parallel, you can program them at which time they come together. And that's very important for cells to grow together. They have to have a temporality as well, and this can be programmed. But not only tissue printing, but we can also do different patterns and stuff like that. One of the things that I'm thinking of is trying to move conductive ink on it and have it as a live way to route between electronic components, for example. So it has to completely to have a different design, and you have your electronic components. And now you have to have these messy wires all the time, and it's not really rerouting. And then even if you use Eagle, you have to draw the routes manually. So what if you can rearrange them and then just show which ones connect to which, and then the routes are computed automatically, liquidly, quickly, and showing if it works or not. A conductive ink can be moved on this one, so I've tried it before. Yeah. Well.
So excuse me for this very basic question. So
No
what
problem.
did we see in the last experiment?
Oh,
So
just
it was
being able to move biological samples. That was the last thing.
Yes, but then the mixing with the blue.
Yeah. So this is a plasmid, and there's a DNA, and they're mixing.
Okay, so it was basically the same with the colors,
Just with that, and technically, if you have different types of reagents, you can assemble DNA.
Okay.
But I'm not able to carry too many things over the border.
Did you say it started to color or something?
That was the previous one.
No.
Oh, here I edited the color myself,
Because
just to make a
that was
difference.
like you put something in, then because it's DNA, it starts to get a color because of this.
Oh, okay. No, this is when you have this already transformed and you add a certain sugar, it gets the color. But in this case, it's not that reaction that added the color. I added the color myself.
Okay.
So they're two different things. Sorry for that. Yeah. And the idea is that when you assemble a piece of plasmid with your DNA, you have a series of steps that you have to follow, and they could be as well followed here. So.
Okay. Thank you.
No problem. Okay. So to wrap it up, I would like to challenge each of you to kind of not be afraid to step out of your comfort zone. I have a lot of questions regarding high voltage. Technically, if you ask an electrical engineer, 300 volts DC is not high voltage. High voltage is from 1,000 volts, and we had a lot of fun in our undergrad building Faraday cages, like making thunders and lightnings around us. And for that we had to use a few thousand volts. So depends to what you're used to. For biologists, for example, making computer programs very complicated, it looks like super scary. For some people, working with some voltage looks scary. For some other people, working with biological samples and making antibiotic resistant bacteria just to change its color, it's very scary. So I want to challenge everyone to just step out of your comfort zone and try to learn as much as possible about what you're doing. And then it's going to be much better. Okay, thank you for attending. And
any new questions about how microfluidics operates and the possibilities of interactions with high voltage and chips and things like that. So again, excellent demonstration. What we'll do now is we'll have an early break for lunch. Lunch will go on until 2 o'clock, and we'll come back in for the technical sessions at that stage. So we'll have to wrap that up now, and we'll see you back here then at 2 o'clock. Lunch will be served either in here or just at the dock just outside here at about 1 o'clock. I'll see if they can get them a little bit earlier or so. Okay? So we'll just thank again, Marilla again. So